Okay, our next speaker is Somnath Basu, who's going to speak about what is transversal string topology.
All right, so I guess I should start by thanking the organizers for giving me this opportunity to talk about this. And I should say that it's been a great experience working with Dennis, and I think what I'm going to talk about today pretty much sort of originates with discussions with him. And I think the original ideas were in the works of Jason and Michael. They're the ones who kind of emphasize that one should look at transversal strings, which I'm going to define what it is. But I think for the lack of time, in case I don't get to the final sort of result, I'll just say, I'll probably just write down the punchline in case I don't get to it before. So basically say aim or theorem so one can use transversal string topology, which I'm going to define in a moment, to detect non-homotopy invariants. Okay. And I think in the talk following mine, Michael is going to use this for the examples of the knot complements in S3. So we'll probably have some flavor of how this thing works. Homotopy invariants. Okay. I'll explain what I mean by this of manifolds. Oops. Okay. So the basic setup is the following: that in the usual setting of string topology, which you have probably heard from Ralph's talk and Moya's talk, where they study loop spaces and homology of free loop spaces, most of the structures that you can get from there are usually homotopy invariants. So here what we do is we just change our point of view and make a geometric choice of loops that we want to study, and we study some certain algebraic structures on such geometric loops, and we see what we get at the end. Okay? So to begin with, I would say that it's one nice way to view a loop. From a loop is a map of a circle to a manifold. You can think of this as a map. I'll just call it gamma tilde from, let's say, 0, 1 to m cross m, such that gamma 0 and gamma 1 are all in the diagonal. Okay? So a loop could be thought of as two arcs. So this is like the folding map. So if you have a loop, then you can just map it using both the arcs, and you get an arc in m cross m, which starts and ends on the diagonal, which just means that these two arcs close off to give you a loop. Okay? So you have this translation. So a picture here, say in M, could actually here, if this is the diagonal, it could look like this. Okay? So this is m cross m. Okay? So what we'll do is we'll just make a choice here, and then we'll work on this setting throughout. So we wouldn't be going back to this picture.
Yeah, right. The starting.
Yeah, so we have x and y, then this is going to be x, x, and y, y. So just parameterize it there. And I think often I'll be talking about unparameterized circles, so it's not going to be parameterized with 0, 1, but up to homotopy, it's the same thing. So that's okay. So, all right. So I think, let me just explain the setup. So now that I've motivated why one would, instead of looking at it here, look at it here. So what I would do is I'd just take Y to be a submanifold, and you have your big manifold X, and you have a tubular neighborhood. Okay. So I wouldn't say what exactly. So this T is going to be the boundary of some small normal bundle of Y. Okay. So think of Y as an embedded submanifold of X, and then I'll just call T a suitably small tube around Y. Okay? I'll just call this the tube. What I mean by suitably small will probably be clear in the context. So now what we do is we do the same thing here. We just look at strings which start here and end here. Okay? But now we make the restriction that whenever the string sort of hits the diagonal or goes through the diagonal, it's transverse. Okay? So let me draw a little more. So let's say something like this. Okay? So we require gamma to be transverse So whenever gamma intersects y, it has to be transverse. Or if you want perpendicular. So if you think about it here, if you look at the normal sphere, it goes through the north pole and exits through the south pole. Okay. So we'll be looking at such strings, and I'll be calling these things transversal open strings. Okay. Well, it's called an open string, pretty much borrowing terminology from physics, one could say, because these are open strings, they don't close up, and it's transverse because it's defined to be transverse. Okay. Transversal open strings, and I'll just denote this by ST, the space of such transversal open strings. Of course, if there is time, we'll apply it to this setting where our y is going to be the M as the diagonal inside M cross M. And then we'll recover the usual loop space scenario. Okay. So, well, what can one do with such strings? Well, first of all, you see that if you have a string like this, it has a point of exit. Then you have a Q, and here you have a Q bar. By bar, I mean the antipode, because I'm assuming it to be perpendicular. So if it goes through the north, it comes out to the south pole, and you have R. So given such a string, you naturally have a map, which I'll just write it this way. Okay. So what I do is I just think of it as, as stacking these kind of chords, and I put P and I put the Q bar of the last point. Here I put Q bar, but then I flip at the last point when it enters. So I have this map. So this is an element of, let's say, something like this, and this could be thought of as an element of 4 copies of the tube, right? And I'll have a little bit more to say later on about what exactly this space is, but that's what it is. This is kind of stratified in the sense what, the elements here are basically have a number attached to them, which is how many times it goes through the diagonal. So it should be thought of as a stratified space. And it has this map where, depending on how many times it goes through the diagonal, it will have as many copies of T. Actually, and for those of you who kind of would like a better notation, this is what actually this is. It's not, you see, these two are not unrelated. They are just the same Q's, but they're related by the antipodal map on T. So you can think of this as a fiber product of T cross T, where you have this antipode match, switching it. So in general, what you'd get is I'll just call this the evaluation map. So you get the evaluation map from ST to what I'd call T infinity, which is basically, you can imagine what this is going to be. If you have strings with more intersections, it's going to be more such things, and you take the union of them. So, if you really want, this is going to be something like, so this is going to be n, this n greater than or equal to 1. Okay. So this is the evaluation map where you just write down the same thing, wherever it goes through, wherever it goes in, and then flip it over. You have a map like that. And you can, of course, apply it to chains as well. So whenever I write this, you can apply chains. You get chains mapping to chains here. Now, what can you do with such a space? Well, the first obvious thing to do is if you have such a loop like that, not here, you can sort of split it at wherever it goes through. So I'll call it delta, which is not to be confused with the diagonal. So this is Q, this is P, this is R. So you get a map which goes from P to Q, map which goes from Q bar to R. Okay. Right? You can just split them. And of course, if you have more than one intersection point, you just go to each intersection point and you split them and you formally add things up. And to formally add things up, you need to work at the level of chains. So I'll be kind of cryptic here, but I think the picture should be clear. So you get a map from here to here, right? So you can basically split them. But again, the question is, it's not quite splitting them and giving you two arbitrary things, because when you split a string, it's not going to give you two things quite far away. It has this gluing property that these two are glued by Q and Q bar. So what's actually going on here is, again, this is like the fiber product. So whatever you get from the starting point of a string here and the ending point of a string here, they're related by the antipodal map. So this is actually a fiber product. So if you want to know the models of chains of a fiber product of two spaces, this is essentially, you can ignore the arrows. It's quasi-isomorphic to what, if you read Milner-Moore's paper, they call it a cotensor product. So basically, I mean, just think of like bimodules over rings. So you have tensor product of bimodules. Just dualize all the arrows. So this is going to be a co-module with a left coaction and a right coaction. And this is just going to be, all this means is you look at all subsets of chains on here and here which has this gluing property. So this is a sub thing of the tensor product, clearly because it doesn't land into things far away. So it has this gluing property. So this should be thought of as compatible pairs, okay, of such transversal strings. I mean, if there is time, I would be happy to explain later on what this thing is, but it's a little technical. But it is a key point in this discussion. So you get a coalgebra in this setting where in this cotangent.
This is a tensor product in some.
Yeah, it's a tensor product in the category of bicomodules where the bicomodules are happening over the chains of the tube, which is a coalgebra. So that's so that's setting. Okay. All right, and so you have one more thing that you can do here, which is not that obvious, but you can imagine what one would do if you have a string like this, right? So what you could do is you could try to resolve this, and just by the usual definition of resolve, when you mean resolve, we want to get rid of the intersection. So imagine if you had a knot, and then you have something like this. There's two ways to resolve it. You can have an overcrossing or an undercrossing. Similarly, in general, if you have the normal sphere like that, then you do not have a canonical choice to go from here to here without avoiding the diagonal. You have to have all the meridian lines to go through. So what you do is you go all the way up to here. This is your normal thing. Use all the meridian lines to flow down to the south pole and then follow across the other arc.
That sphere is supposed to link the submanifold. It doesn't touch it, right?
Yeah, so this picture is not quite, I mean, I can only draw the knot picture, but so let me draw that picture. So I think this one in this case is going to be like this. There's some sign issues there. Something like this. You have overcrossing and undercrossing. In general, if the normal sphere is of higher dimension, use all the meridian lines to go from here to here, and then you follow through the usual way. So that's, you get a change. So that's why I have to work in chains here as well, because the dimension typically goes up if this is not a knot or some other example. So we have this R which can be applied at the level of chains as well. So now I think I can state what I, so of course there is a shift of grading that I'm sort of hiding because it's, again, if there was time, would have got into this. So this is sort of stratified, and then you have a star here. So there are two things that you can play around with. So there's a shifting going on. But after that shift, what you do is you form this. So this just means you take your usual chain boundary. So given a chain, you can take its boundary. This R means you stick in this. So whenever you see something like this, you can do two things. You can either resolve it or you can take its boundary. So that's your new operator, which can be shown to be a differential. It squares to 0. And this is the one that I have here. Here, it's the splitting. Right? So this is a, one can check that this is the differential graded coalgebra in this setting of this box product. So it's a differential graded coalgebra in the setting of bicomodules over chains on the tube, if you want the technical term. But that's basically what you have. Okay, but what's the point? Again, remember that we said we can detect the non-homotopy invariants of manifolds. In these examples, what we're trying to detect, so here, so aim is detect, let's say, the homotopy type of x minus y. So you want to detect the homotopy type of the complement. So we somehow have to get hold of the complement or some construction of the complement from these things. So
this may be confusing, but the complement is not a homotopy invariant in the case of the diagonal. So that's
so right.
The homotopy type of the complement is not a homotopy invariant of manifold.
Right. So that's probably a good point. So one can check that there exist homotopy equivalent manifolds M and N. For example, three-dimensional length spaces such that M cross M minus M is not homotopy equivalent to N cross N minus N. Okay. So even though the manifolds are homotopy equivalent, the 2-point like 2 points floating around in a manifold will not be homotopy equivalent to this. And this is not just because of some torsion, it's true over Q. So that's basically what we're trying to detect by these considerations, but we are not quite there because this is a huge space and a huge construction. So what one would like to do is one would like to get hold of some sub thing sitting inside here, namely the ones which start and end and have no interior intersections. Okay? So if you restrict yourself to A, so this is, I think, what we have been calling the chord space. So this is basically all transversal open strings which look like this. So it starts on the diagonal, ends on the diagonal in the example, and has no interior intersections. And you notice that there's a map from here to T cross T, namely given something like this, P and this is Q. You can map this to P comma Q bar. Okay? Just flip the other one. So there's an actual map to the T comma T, and I'll call this small evaluation. And if you look at evaluation inverse of P comma P, well, this is essentially going to be the fiber, but we don't have it. This is going to be all loops which start at P and end at P bar because of this flip at the end. So this thing here is going to look like things which start at P. I'll just draw it from the behind. This is P bar. Okay? So it's all things which start at P and end at P bar. So one can think of this essentially as the base loop space of the complement. Okay? Because if you choose a meridian line on the normal sphere, it's basically the base loops at P, for example. So this is, and one can show that this also has some this also detects the homotopy type of x minus y. So for example, whatever we wrote down here is a result of Longoni and Salvatore by minimal models and massive products, which you have seen in John's lecture, tells you that this also detects the homotopy type. And so essentially this is where we're trying to get to, but that's what we have. So what one can do is there's a functorial and natural construction called the Cobar construction, which starts with a differential graded coalgebra. And forget the differential graded part. It has a coalgebra as an input and gives you an algebra as an output. So the usual examples that you might see is if you take the chains on a space, it's a coalgebra. And if you apply the Cobar, it gives you the chains on the base loop space. Okay? So I think the original construction is due to atoms. So what we do is apply. So the thing is, Cobar is also denoted by the same symbol, capital omega, so I'll just write Cobar. Okay. So Cobar of C star of this. I'll put a bar. I'll explain what the bar means. The bar just means you mod out by your ground co-ring or your ground coalgebra, because here the chains on the tube is like your K in the usual construction, or Q. So you mod out by that, and there is a quasi-isomorphism to. So all this is saying is that if you start off from that big construction, apply this functorial setting. I'm not going to say any more what this thing is, but you can recover the chains on the chord space. I think this is what I denoted. Okay? And not only that, you basically have this map to T infinity. Where did I write it? Here is it? Oh, in the middle. Oh yeah, here. So if I apply chains here to chains there, there's a natural map there too, right? So still call it EV. Cobar. Okay. But of course, at this point, you should ask, okay, fine, I told you that Cobar takes a coalgebra and gives you an algebra. And we know that this is a coalgebra by what I described to you before. But what is the algebra structure here? It's supposed to give an algebra, right? But that's essentially clear from, it should be clear from this picture, because what it says is if you have two chords which have no interior intersections and they have this gluing property, then you can apply the same R, but now think of it as a multiplication. So you go all the way up to here, and then you use the meridian lines to flow along. So the picture will be pretty much, so if you have something like this, so think of this as gamma 1, gamma 2, and R. I'll just call this star R, I think, but R, let's say, which will just give you this. And you go here, and then you just follow along. Yeah, this is, again, like not the right dimension to draw the picture in, but, and then it closes off at here. Okay? So that's your R. So you can think of it as a multiplication on the chords with no interior intersections or as part of a differential. And this is the algebra structure that we mean here. And again, this is again in the setting of this box, because you cannot just glue two things far apart. You can only glue things which have this flip property. Okay? So once you get to this, now we should kind of go back and look at where do we have the A? Here. So we know that the fiber there is the base loop space. So essentially, what this is telling you is that starting from here, apply the Cobar, you get a way to get hold of the chains on the fiber of this. And that has an algebra structure, namely given by this twisting, because this has the same R-twisted algebra structure. So what you finally get from this is that, well, the fiber models models a twisted product. Namely, if you think of that as P, then what happens here? If you have two such loops, then you go along one loop and then you use all the meridian lines to go to the other one, and then you go along the other loop. So that's what you get. And again, one can show that it's pretty much the same proof as transferring this result to that, but now you add in the extra twist. And again, it uses minimal models and massive products. And one can show that this twisted product over here also detects the non-homotopy invariant between the two length spaces. And that's essentially the idea. So you start off with this, you just stick in the extra R, and then, so for those who are aware of the bar-Cobar thing, this quasi-isomorphism here is basically a bar-Cobar adjunction. Okay, but I mean, I don't know how much, probably don't have much time, right? But I mean, that's pretty much.
Is it worth saying just take a minute and say why this isomorphism is true? Because R and A is the strings. So
yeah, right. So I guess
that's
right. So I guess the proof of this.
With the picture. Yeah.
Well, so I think the bar, right. So where's it? Oh, there. I'll probably say it here. I don't think I'll need this.
There's another board.
Right. So I think the idea is that this chains on this transversal open strings could be thought of as B. So for people who know classifying spaces, think of B as a classifying space functor. Given a group, it gives you B. The same thing of a bar. Yeah, that's probably better. So C star of A. So again, here, when I say bar, I mean in the setting where you use the box instead of the tensor. So this we know is an algebra using this box product. And the bar here essentially means, what do you do in a tensor product? You just take, like more stuff like this, okay? And that's basically, and you take a direct sum over such n, and that's basically your bar complex. So what this means pictorially is that you're this box is telling you that you take things and you stick in things where you can only glue things which are compatible. That's what the box does. So if you have a bunch of these, you just stick in. So this will be A box, some chains in there. If you take all of them, you're essentially recovering the chains, and the transversality is taken care of just because we're assuming it goes through the north and enters through the south pole. And so pictorially, this is like the bar, and you just have to check that it's a quasi-isomorphism. And this proof here is saying if you take the bar of something and then take the Cobar, it essentially gives you back a nice free model of the thing you started off with. So, but I mean and this bar Cobar thing pretty much works in a much general setup. We just apply it in this setting. Okay. But yeah, I'll probably stop here. And one last thing, I think I'd like to thank the organizers for what has been a very efficiently run conference so far. So thanks for that.
Any questions or comments?
So in the overcrossing, undercrossing picture, do you need a negative sign somewhere to get
probably not. I mean, it's like C0 it's like chains on S0, but I don't think you need a sign. It's just going to be that plus that.
Well, it seems to me a zero-dimensional sphere consists of 2 points of different signs. It's a bunch of.
Yeah, but I guess we had this discussion like before at some point, but I don't think I think you'll see what happens in that case in Michael's talk in the talk following this, where he's going to apply two knots in S3. So, but I think the one with the right sign where you take both of them to plus works out fine. So, yeah, I mean, I agree that there is some ambiguity where maybe one can ask a question, but I don't know.
So, is there a way that these like non-homotopy invariants can be fit together with like older like homotopy invariants that we called string topology before?
Maybe, but I think the thing is like this assumption that the things are transversal. That's sort of adding a geometric input like to the like submanifold on which you're choosing. So, I mean, it's probably like something like worthwhile thinking about, but I haven't like really thought about it. I mean, maybe one has to enlarge those discussions to like these settings, because usually there you actually work on these loops and you do not think of these kind of things, because for example it's very hard to imagine the rotation operator on this setting because it's kind of like a sliding thing happening on the diagonal, but it's very easy to imagine it on the loop space setting, right? So I don't know how much of those things you can, let's say, easily carry over in this setting with these geometric inputs, but maybe one can do that, I guess.
Thanks.